This is a What the Physics video. We're finishing up the Big Five acceleration equations, and we are specifically talking about free fall. So free fall is when an object is falling because it is being attracted to the Earth due to the Earth's gravity. Gravity is pulling on the object. The object is also pulling up on the Earth, but the Earth is much more massive, has a lot more inertia. You can hardly notice its movement at all. The acceleration due to gravity is little g, and that's 9.8 meters per second squared. If you want to say downwards as negative, then you would say negative 9.8 meters per second squared. You do not have to say that downwards is negative. It all just depends on what your reference frame is. Realistically, most people do say downwards is negative, but just because most people do that doesn't mean AP test is not going to try to screw with you and say, hey, you know what, today I've decided upwards is negative. So that's nice of them, isn't it? We talked about the initial and final velocities. Sometimes they're given without being totally obvious about that. Okay, and what I mean there is, let me switch out the screens here. Oop. Here we are. So if I have a water bottle, and I'm holding a water bottle in my hand up about my head level, and I'm going to drop it to my other hand, which is about my waist level, somewhere around there, and we'll just assume that is a 1 meter or half meter drop. Okay, there's my water bottle. You say, oh, that's a, yeah, shut up. All right. So it's going to fall downwards, yes? And it's got a displacement on the y-axis. Now, this is one of the reasons I don't like to use delta x, because you say, there, it's not on the x, it's on the y. Okay, so I can use delta y. You say, there, none of the equations I have include delta y. Well, guess what? You can take out the x and put in the y. Okay, but that kind of throws people off. So, all right, so, and the velocity up here is the initial velocity. And down here would be some final velocity. I usually say VF, but AP wants you to say V. And then it's accelerating downwards. And I'm going to say, give my coordinate system here is positive and here is positive. So I'll use the standard up is positive. Not required to, but that's what I choose to do to get this point across. So what can I solve for here? I can solve for the time, and I can solve for the final velocity. Let's list out my variables, yes? Initial velocity, final velocity, acceleration, displacement on the y, and time. What information do I have so far? The acceleration due to gravity is little g. You can also say it's negative 9.8 meters per second squared. Good. What else do I have? Displacement. What is that? Half a meter. Okay, down. Yes. Okay. It is 0.5 meters, but it's going downwards. And we said downwards is negative. Thus, it's negative 0.5 meters. You'll see in a moment, if you forget that negative sign and you try to plug stuff into certain equations, you're going to have to try to take the square root of a negative number, and then that's a problem. Now, most of the time people are, that's a good indication, like, oh, shoot, I forgot that, and they go back. Or sometimes people just wave away the negative sign, like, oh, it disappeared, I don't know how. But anyhow, let's be good, right? And then someone said something else. The initial velocity is 0, okay? Because I simply dropped it. I didn't throw it downwards. Okay? I didn't toss it up in the air. Let's go ahead and solve for the final velocity first. So that means I'm looking for the final velocity and I don't care about time. Okay? If I don't care about time, which equation is that going to be? The velocity final squared, yes. Velocity final squared equals velocity initial squared plus 2 on your papers it says 2AD, but we're going with delta Y. Okay. Do we have to do any rearranging? Not really. V final is already on one side. Yeah, I'll have to take the square root, but that's pretty obvious. And hey, while I'm at it, is anything equal to 0? Because that's always cool.
Yeah.
Okay, what's equal to 0? Okay, so that makes that go, that's going to be really easy. Final velocity is equal to the square root of 2a delta y. Good so far? I plugged that in for the information I'm given, and that is going to be square root of 2 times negative 9.8 meters per second squared. Oh, I'm running out of space. And times negative 0.5 meters. Okay? Tap into your calculators, please. I don't have one on me. Tap, tap.
Plus or minus 2.213594.
Okay, I'm sorry, say it again nice and loud. 2 who?
2.213.
2.213. I think that's enough decimals. What are the units? Meters per second. And if you notice, inside the square root was meters squared per second squared, right? Then we take the square root of meters squared per second squared, that's meters per second. So that's good sign, right? Okay, awesome. Is that the final answer? That's the final velocity, yes? There was something very important that you had said right before the number. Plus or minus. Anytime you take the square root of something, it's actually the plus or the minus. No, I don't like minus signs, so I'm not going to include it. Okay? Which way is the object going? Downwards, and we define downwards as negative. Okay? So we do have to include the negative sign. So mathematically, there are 2 possible answers, but in terms of physics, there's only one reasonable one. Yes? Okay. Yes, dear.
Yeah, I got it.
Oh, I didn't do the number crunching. What did you get?
Yeah, 3.13.
3.13?
Yeah.
Okay. You want to double check yours, sir, just in case?
But it's also times 2.
Okay. All right.
It's a
So
2 in the
I'm glad you guys are all being attentive to this. All right. All right. So the new answer is negative who? Negative 3.13 meters per second. Okay, great. Okay, I'll call attention to that because this is being recorded. That's fine. And folks, people make mistakes. It's not the end of the world. You're showing everything else, then that's good. Okay, if you're not showing what the heck you're doing and you give the wrong answer, I don't know what you did. But if you're showing logical steps, that's good. Okay? Speaking of logical steps, I drew a picture, but you know what I didn't do? I didn't draw a graph. Can I draw a graph of this situation?
Yeah.
To help us understand what's going on? What, you say what type of graph there? Position time graph, velocity time graph, acceleration time graph? Well, you could draw any of those. Let's do red. Okay, I'll say that's Y, T, that's V, T, that's A, T. What do you got? Any of these you can fill in? You don't need actual numbers, just basics. Yes, sir.
The acceleration is always going to be like negative 9.8.
Yeah, the acceleration is negative 9.8 because we defined upward as positive. Okay, so, okay, that acceleration time graph, while accurate, isn't really helping us understand much. Okay? All right. Yes, sir.
The velocity time graph has a negative increasing slope.
Negative increasing slope. Mm,
No, negative constant.
I do not agree with that.
A negative constant.
Yes, sir? Okay, all right, hold on a second. So the initial, because I don't think the recording can pick you up. The initial velocity is 0. Okay, so I'll mark that right here. And then the final velocity is some negative value. I didn't need to calculate that in order to realize that. Right? I know it's going to be going downwards. So it's going to be down here somewhere. Okay? Now, what is the curve going to look like? Is it going to be a straight line or what? Straight line, yes, indeed. The velocity is, well, I missed it, but there we go. The velocity is increasing. It's negative, but it's still getting larger, right? So the slope of the velocity is negative and constant, just like the acceleration is negative and constant, right? Okay. The velocity itself is increasing, so we got to make sure we're using the right descriptions for the right things. Good. And then finally, what would the displacement time graph be? Or, position time graph be? Yes. Exponential. Okay, so all right, that's an awkward. All right, it'll start at 0, assuming we define my top hand as 0. Okay, and it will be going down something like this. There's supposed to be a curve there. Okay, and it's first going rather. There's a small change in position at first, and it keeps getting larger and larger and larger. If we were to take the slope of this, you'd see that the slope here starts out at 0, and then it's getting bigger and bigger and bigger. Okay, it's negative, but the slope itself is getting larger, just like the velocity is negative and getting larger. Okay? Usually, I would say if you had to draw a graph, they just ask for one. Go with the velocity time graph. That's usually the most useful. As we can see, the acceleration, I mean, yeah, that'll take a second to do, but it's not terribly useful to. Yes, dear. The velocity in this one is supposed to be a straight line. I can improve that a little bit. Okay. Sometimes when I'm drawing to the side, it's a little challenging. Yes.
What happens if you have something that was like moving in like a negative velocity, but its acceleration was decreasing?
Okay. If I'm moving in the negative direction.
Yeah.
And then the what?
Like it was like in the negative for the velocity time thing. It had a positive slope. What would the acceleration time look like?
Okay. So the question was, so this is a different setup right here. Okay. The question was, if I have a velocity that is negative, okay, so somewhere down below the x-axis, velocity that is negative and the slope is positive. Okay, so something like this, you mean?
Yeah.
Okay, what would that mean? Okay, so the velocity is negative. What does it mean to have a negative velocity? I'm going in the negative direction. There's nothing truly special about that. Okay? It can still mean I'm going downwards if I say downwards is negative. Or if I say I'm driving a car and we usually say forward is positive, then in this case I'd be going backwards. Yes? Okay. Then the question is, what does this? So we've got a negative velocity, and what is happening to the value, the absolute value of the velocity? It is decreasing. So that means I am doing what? I'm slowing down. Yes? Okay, does that cover your question? Okay. Now, in the case of acceleration due to gravity, I do have situations where I'm slowing down. Okay, not specifically in the negative direction, and this is getting ahead just a little bit. Okay, but when I am, if I were to toss something up in the air, if I were to toss this water bottle up into the air, okay, the velocity in that case, it would be positive for the first part. Eventually, it would stop going up and then it would come back down. Yes? Okay, and as it's going upwards, it would be slowing down. So it would be positive, and then this would be what we call the peak. The peak is at the highest point. Okay? Is at the highest point, is it going to go up any higher? No. Has it started to fall back down yet? No. So for just a split second, the velocity is 0. I'm not saying I throw a water bottle up in the air, it gets stuck. Okay? I'm saying for a split second, it's 0. But there's still the acceleration due to gravity, so it's going to still cause it to accelerate downwards. Okay? So there. This would be a velocity time graph for an object tossed upwards, and then it comes back downwards. The acceleration time graph for that would still be the very boring one, just like before. Okay? That's why I say go for the velocity time graphs. They're typically a bit more informative. Yes?
Wait, so negative acceleration can mean both, like an acceleration in negative direction and an acceleration? Or, like, how would it look like if there was acceleration?
Okay. So the question was, it seems to me your question is about negative acceleration and deceleration. Okay? And I believe I had mentioned earlier on, I would encourage you to stay away from the term deceleration. Okay, the reason being is, and you'll tell me right now, what does deceleration mean? Slowing down. Okay. So it means you have a negative acceleration, right? Okay. I just got you. Slowing down and negative acceleration are not the same. They are the same if you're moving in the positive direction. Okay, so if you're driving forward, here, this isn't really what I planned on talking about, but we can still keep talking about it. Okay, if we are driving forward, car, this is the direction of the velocity, and this is the direction of the acceleration. What does that mean we're doing? We'll say to the left is positive. We are speeding up. Yes? Okay. What if the velocity is still this way and the acceleration is now that way? What is that going to mean? Slowing down. Okay. That's when everyone says, oh, we're decelerating, right? Sure, maybe, not really. Not necessarily. Okay, because once again, decelerating and negative acceleration don't mean the same thing. Okay, but people treat them like they are. What happens if we're going in the negative direction? If we're saying to the right is negative, so the velocity is negative, and the acceleration is also negative. Now what? Are we speeding up or slowing down? We're speeding up. Okay? But if we're going in the negative direction and we're accelerating in the negative direction, are we decelerating? No. Okay? And I could do the exact same thing here as well. Still that way, and then this way. Okay? In that case, I'm moving in one direction, I'm accelerating in the opposite direction, I'm slowing down. but I'm moving in the negative direction. So does that mean I'm decelerating even though my acceleration is in the positive direction? And your head explodes. Okay?
Yeah.
So it's easier, in my opinion, when you're talking about you're accelerating, you'd say you're accelerating, and then clarify that by saying you're speeding up in this direction, you're slowing down in this direction, or something. That's not specifically a standard way of doing it, but that's what I found is a pretty helpful way of doing it. Okay? All right. Let's like I said, this is cool stuff, but it wasn't exactly where I was going. So let's continue on with finding the time. So I can still use the same information as before. This time, I'm going to be solving for the time, and I'm not going to care about the final velocity. Say, why don't you care about the final velocity, Fair? You know what it is now. Yes, but in case I made a mistake, I'm going to try to avoid using something I just solved for, if at all possible. Say, yeah, sure, cool. If I don't care about the final velocity, which equation is that going to be? In our list, it's going to be the third one, yes. Okay. It comes up as D, but remember that's going to be delta Y. Okay. Delta Y equals the initial velocity, V0 times T plus 1/2 AT squared. Hopefully we agree on that equation. You say, cool in the gang, let's go ahead and solve for T. Let's see, the first thing I'll do is, what? How can I solve for T? Oh, this is embarrassing. I'm on video too. Dozens of people might be watching this video in the next 10 years. Dozens and dozens. And I've made a terrible mistake. How can I solve for this T?
Substitute.
What? Substitute. Maybe I don't know. You'd have to do a quadratic thing, right?
Oh.
Yes. You learned that song, the Pop Goes the Weasel.
Oh, yeah.
I just know quadratic
X
formula.
equals. Oh well. Whoa! Oh, I have to know this. Good. I do as well. But yeah, look at me. Okay. But what I'm getting at is, in math class, I don't know where they specifically teach you. I know they teach you this in some of the math classes, like Algebra 1. If you take it here, I don't know if they teach it at other, like middle school and stuff like that, but it's to the tune of Pop Goes the Weasel, right? No.
I never learned about quadratic equations.
All right, you know what the equation is, yes?
Yeah.
Tell me what the equation is.
Negative b plus or minus
Oh, slow down. Okay. All right. X equals negative b plus or minus square roots b squared minus 4ac. Yes, so now we get to sing it with Pop Goes the Weasel. X equals negative b plus or minus square root b squared minus 4ac all over 2a.
Oh my
You
god.
guys never heard that before?
No.
We're all in better trouble.
I don't know what that insult means. Anyhow, I don't know if it's even an insult. I don't know if it might be cool in the game. I don't know. The point is, you have to use this quadratic that you've never heard sung to Pop Goes the Weasel. Well, now you have a new song to have fun with. The point is, that's a real pain. And I don't feel like doing that. So I'm going to try to find an easier way of doing this. You know why? Because there is an easier way. Anything up here equal to 0? Initial velocity. Ha-ha! Boom, 0. That means I don't care about that t because it's gone. Oh, yeah. So, delta y equals 1/2 at squared. Ooh, can I solve for t now? Yes. What would you do?
Divide delta y by 2.
Divide delta y by 2.
Oh, multiply.
Multiplying. Okay, so 2 times delta y over a equals t squared, right? Square root both sides. Yes. Yes. Okay, now plug in. Just kind of shimmy over here. And everyone is checking their work, yes. 2 times negative 0.5 meters divided by negative 9.8 meters per second squared. Yes. Meters cancel. I've got 1 over second squared, so that'll just be second squared. When I take the square root of second squared, that'll be seconds. So please tell me what the numerical value is. 2 times 0.5 is 1, right? Okay. All right. What you got?
Whatever, 9.8.
Give me a decimal, please.
0.319.
I'm not a math teacher. I like decimals. What?
0.319.
0.319, and that's going to be seconds. Yes. Right. Questions on that? Good stuff. Now, the whole reason I wanted you to do this is, all right, so that was for half a meter. What if I dropped it a full meter? Say, ooh, what would happen then? Just multiply by 2. It'll double everything, right?
Nah.
Haha! No, suckers! Okay, so this is now negative 1 meter, and this is getting really cluttered, so let's extend page. Okay, so initial velocity is still 0, final velocity, or v or whatever, is one of the things we're trying to figure out. Acceleration is still little g. Displacement is now negative 1.0 meters, and time is still something I'm trying to figure out. Okay, luckily, because I am awesome and I rearranged the equations before, I can just say, hey, v equals square root of 2a delta y. Plug it in, plug it in. And calculate, please.
So are we saying that acceleration is negative 9.8?
Yeah, acceleration is still negative 9.8, yes.
So 4 point.
So using this new version, it's 2 times negative 9.8 meters per second squared times 1.
Negative 1.
Meter, yeah, that totally ran out of space there. But, okay, what do we get?
4.427. Meters.
Say again?
Yeah. 4 point.
Negative 4 point who?
4.27 meters squared.
Meters squared.
Wait, not
Meters per second. Oh. Okay, now that's way too many digits. That's okay. I would like that many digits for right now. Okay? How does this number compare to this guy here? Twice as much, right? Yeah! No. If I look back at my original equation, this guy, what was the relationship it was telling me? It was saying V final squared is proportional to delta y. So guess what? When I double the delta y, it does increase the final velocity, but they're not proportional. Anyone guess what the number is? Square root. Usually someone would say, it's a square root, fair? Yes, okay. Square root of, square root of fair. I don't even know that. No, square root of 2. Okay? Because there's that square in the relationship, okay? So simply doubling the distance is not going to double the velocity. Likewise with the time, which I have to scroll up for, delta y is proportional to t squared. Okay, so that's going to give me a different value. If we actually solve for it, I see there. Use black. Okay, so t equals square root of 2 delta y over a. It's the exact same equation as before. Plug it in. And don't just sing the song, actually plug it in, please. 2 times -1 meter divided by -9.8 meters per second squared equals
0.451 seconds.
0.451 seconds. Does that sound good? Okay. Guess what the relationship there is? Square root of 2, yes. Okay. So you say, oh, if I double the distance, then that means the time is going to double as well, right? No. Not happening that way. Okay? I just want you to realize some of the relationships that are involved here. Okay? Okay. Now, it's important that you realize something, folks. You may not have understood, or you may not have realized this before. Some of you might have noticed this before, I don't know. I look around the room, and I see some people that I am guessing that some of you are under the influence.
I swear to under the influence, I am not goodness.
Thank you, sir. You are definitely one of the ones under the influence. Okay? I'm not saying your name, so it doesn't matter, but you, yes. And everyone's like, me? Oh, how do you know? And yes, over there, you are also under the. You know what? Right now, I too am under the influence of physics. Okay. Is that what they're calling it on the streets? Right. Okay. You say, oh, fair, you're recording yourself right now. You're saying that you're under the influence. Yes, I am under the influence. And I've been under the influence for a long, long time. For longer than I can remember. And you might be saying, like, yes, that's why you can't remember very long. You've been under the influence, right? I say, no, what are you talking about? You've been under the influence for goodness knows how long as well, right? We're all under the influence, folks. Yet you're giving me all these wacky grins. What are you thinking about? We're under the influence of gravity, right? What were you thinking, huh? Yeah, physics. Okay. All right. We are under the influence of gravity. As I mentioned before, the Earth pulls down on stuff. Stuff pulls up on the Earth. But because that stuff that we're usually talking about is so teeny tiny compared to the mass of the Earth, we don't tend to pay any attention to the Earth's movement. The force is still there, still pulling up on the Earth, but okay, we don't pay attention to it right now. We'll discuss it later on. Okay, because this pen that I'm picking up right now, my grading purple pen, is a small mass relative to the Earth's mass. I can call this a test mass. If I drop it onto my desk, it will demonstrate the Earth's gravitational field. It is downwards, and I could do some calculations and say, oh, 9.8 meters per second squared, yes? And I go to the other side of the room, do the same thing, same results. I go somewhere else in the room, same results. If I go to another classroom, same results. This is a very, very special pen, right? I paid a lot of money for this pen, but it was worth it for the physics, right? I could go anywhere in the world and drop this pen and figure out the acceleration due to gravity, yes? Is it truly a special pen? No. Okay, I mean, to me it is. I have an emotional attachment to it, whatever. You could do it with one of your pens, or pencils, or water bottles, or apples, or I would not recommend small children or anything like that, but I mean, technically, you would fall down at 9.8 meters per second squared as well, right? But it's kind of the landing that's a problem, right? Okay, so I would discourage that idea. But it still will work. Car goes off a cliff. It will go downwards at 9.8. But don't tell me you're going to do a lab on this. Okay, so any one of these things can be considered a test mass because their mass is small relative to the Earth's mass. Okay? This also is the case if we toss an object up into the air. It goes up, eventually it will come back down, for the most part. Comes back down because of the acceleration due to gravity. At the acceleration due to gravity, it comes back down due to the Earth's gravitational field. Okay? You ever toss a ball up in the air? What happens? It comes back, yes. Okay? You toss it up higher, it's still going to come back down. You would have to toss it really, really fast in order for it to not come back down. Okay? That is not something I understood when I was a little kid. I remember being in my family's backyard, and I had a tennis ball, and I was tossing it up higher and higher, and I threw it up. I threw it really, really hard once, and I kept trying to throw them straight up and have it just fall straight back down just so I could easily catch it, right? Well, I guess I must have thrown it at an angle because I didn't see it come back down. And I'm just like, whoa! It didn't come back! And then I didn't see it, I'm sure it was just sitting on the ground nearby. I didn't see it until the next day. And I'm like, it took that long! Wow! That's amazing! No. Doesn't take that long for objects to fall, right? And they will fall. As they're going upwards, the velocity, if we're saying upwards is positive, the velocity is positive and it is decreasing until we get to the tippy top, which we already called the peak. The peak is where the velocity is 0, just for a split second. And then as it goes back down, the velocity is negative. The velocity goes from positive to 0 to negative if we toss a ball up in the air and let it come back down. What's happening to the acceleration? The acceleration is constant, 9.8 downwards. The acceleration does not go from positive to negative and 0 and stuff. Okay? That is a very common misunderstanding. You throw a ball upwards, and it goes upwards and it downwards, right? The acceleration is always little g, and it's always downwards. Now, some other cool stuff about the speed. This speed right here, whatever that value is, it's also the same speed right here. Okay, if I toss a ball upwards at 10 meters per second, and I catch it at the same height, however long later, it's going to hit my hand at 10 meters per second. Downwards, but if I'm talking about speed, they're the same. If I were to toss them at 20 meters per second, they'd come back and hit me at 20 meters per second. Okay? This speed here is the same as this speed here. I'm not saying this one is the same as this one. I'm not saying that. Okay? But at the same heights, they'll have the same speeds on the way up as well as on the way down. The velocity here is 0 for a split second. Acceleration is not. Acceleration is not 0 here. It's always 9.8 downwards for an object in free fall. Okay. Good. All right. Now, this is making basic assumptions. Your textbook talks about what assumptions are you making. Some of the assumptions are there's no air resistance. Right? If there were air resistance, which is something we'll discuss later on, then the speeds wouldn't be perfectly lined up like that. Okay. All right. Good. We got a falling brick example. This is very similar to what we just talked about a moment ago, so I'm just going to let you do the example stuff yourself. Okay. Yes, sir. Sure. All right, and then finally, the last slide here is object equality. I said if I have this pen and I drop it, it'll fall. It'll fall at G, yes? Okay, if I use this water bottle, it'll do the same thing. You say fair? No, it won't, because the water bottle is more massive. True. So what? The mass of the falling object, as long as it's very small relative to the thing giving off the gravitational field, aka the Earth, the mass is not going to affect how the object falls. We're ignoring air resistance, but the mass does not have any effect on how the object is going to fall. So whether I have a really light object or a really massive object, it will be the same thing. Now, you might have seen situations where more massive objects seem to be falling faster. Okay? A leaf versus an acorn. Okay? An acorn is slightly more massive than a leaf, unless it's a really big leaf. Okay? That would be because of air resistance. Yes? Okay. If you look at the acceleration equations, you don't see mass in there at all. Does not affect. Okay? If you do not believe me, say, fair, I know things that are more massive are just going to fall faster. Fine. We'll just drop it.
Fair.
Ah! See what I did there? Ah! No, really, we are going to drop it. We're going to drop things then. Well, I'm going to drop things.
Kept cooking the pencil.
Okay, so let's see. I'll have to describe these scenarios because, of course, the people that are watching this video, that is to say, both of them,
Are you playing kickball?
can't. No, we're not playing kickball. Who? Okay.
Well, there's one way
They can't see what we're doing. So what I need to do is get myself a tennis ball. Excuse me, please. It wouldn't be fair if we played kickball.
Yeah.
You got too many skills?
No. Fair.
No, I'd be fair. Okay, yeah, that was clever. Okay, so I have a tennis ball and a four-square kickball in my hand. Can anyone verify this is a tennis ball?
Yes.
I don't think you have anything.
Here. A real. Oh, I don't know what you're doing. It's a tennis ball. Okay. This is a kickball, yes?
Yeah.
All right. So I'm going to drop them from the same height at the same time. If you want to move so you can see them hit, that's, the exciting point of your day. Fine. Okay. So ready? 1, 2, 3. Okay. They hit the ground at the same time, yes?
Yes.
Yes. Okay. Remember, the people listening to this can't actually see it happen, so you have to be their eyes and ears for them, right? Now I have the same tennis ball and I have a basketball. Anyone want to verify this is a basketball?
Yes, sir.
It's a basketball. Okay, fine.
It's basketball.
Oh, okay. You just came up and touched it.
It was already.
I mean,
Can
that's all
confirm.
I smelled it too, but you didn't know.
You smelled it. Okay,
It's
well,
already verified.
that's nice to hear. Let's see. So same height, same time, and all right. Hit the ground at the same time. Yes? Yes. Here I have a softball. It got kind of mucked up. That's why the athletic department was like, here, go ahead. Thanks. All right. So once again, the same tennis ball as before, and the softball, and they hit the ground at the same time. Yes? Yes, indeed. All things keep hitting the ground at the same time. I have a volleyball. Let's see. They hit the ground at the same time. Is there a head? Yeah, it's a smiley face. What? It's a volleyball with a smiley face on it. Yes. I've got a Little Mermaid bouncy ball that I have here for when my kids are here. Let's see. Same height, and they hit the ground at the same time.
Ariel has her face washed.
And Ariel, that's very pleasant. Okay. Let's see. Ping pong ball. Woohoo! I got too hardcore and smashed it. Okay, it's still fine. Once again, here we go, physics. Go ahead, right? All right, and all right, hit the ground at the same time. Oh, it's bouncing away. Okay. Let's see. Anything else? Anything else? I got the basketball. You say, all right, fair. Yeah, I guess that I believe what you're saying, but it wasn't very impressive. I mean, all those things are different size, different feel, different consistency. Masses were slightly different, but not that different, right? You need something more massive, like, I don't know, maybe
He's got
a bowling ball. Yes, indeed. Yes, indeed.
Dude, it's gonna be arrested.
Okay, we'll not go through the floor. I've done this before. Yes, Dave. Sure. Yeah. Before you. Yeah. Okay. Oh, they love the teachers underneath this classroom. Love me.
Probably Spanish. It's Spanish. It's okay.
Okay, I'm only going to do this once. Okay, so I will do it.
Should I film this?
Oh my God.
Okay, ready? 1, 2, 3. Okay, hit the ground at the same time. Yes.
Yes.
Woohoo! So what do we learn from this?
Physics is.
What did we learn? What did we learn, folks? I just dropped the bowling ball. Hey, answer the question!
Oh my God.
There you go. All right. Yes.
Oh my God.
You should have aimed it.
The greatest presentation ever.
Oh.
And everybody loves physics. Bye-bye.
What the